Good morning. Assalamu alaikum. So for today's lecture, we are going to continue with lecture 8. So in our lecture before the semester break, we have covered the topics of laser diode. Okay, in which in that lecture, we have learned about the principle, the basic principles of laser diode and how the laser diode fundamentally work as a light emitter. Okay, if we can recall back the terms of stimulated emission, the population inversion. So these are the things that related with the laser diode. So for today's lecture, we are going to continue with this slide, which will be covering the topics of laser diode characteristics. Okay, light characteristics. Okay, so the first characteristics for a laser diode light is a monochromatic. Yeah, it's a monochromatic. Sorry. Monochromatic. So what is meant by monochromatic? Monochromatic is a condition, is condition whereby the spectral width of the radiated light is very small, is very narrow. Yeah, it's very narrow. Okay, that is the spectral width. Yeah, that's what meant by monochromatic. And it can be said that the line width of the laser diode is very small, in which is about 10 or hundreds of nanometers as compared to LED. Yeah. So for LED, the spectral width or the line width is quite big, okay, as compared to a laser diode. Yeah, this has been covered in lecture 7 before. And the second characteristics for a laser uh, light produced by laser diode is that the light is said to be well directed. Yeah, well directed. Okay, so well directed means that the light radiated is narrow. Okay, and the beam or the light is said to be well directed, in which the light can be easily launched into the optical fiber. So in comparison with the LED, the power emitted by the LED is having a Lambertian intensity distribution, remember? Okay, Lambertian intensity distribution. So this is uh, the profile of light produced by the LED. If you can recall back, you can refer to lecture number 7. Okay, so this is the intensity profile of the LED, which is based on the Lambertian profile of light. Okay, so it can be said that the radiation is not narrow, it's quite wide in terms of the radiation angle. So for this particular case, it can be said that for the LED, the launching of light, the coupling of light from the laser LED to the fiber is not it's not effective. It's not effective as compared to the laser diode. From these second characteristics, can be said that the effectiveness of the light launch into the optical fiber is very good due to the fact that radiation of light or the profile of light is very narrow. Okay, number three. Okay, number three is that the light produced by the laser diode is very intense. It's very intense and it's power efficient. Okay, power efficient and intense, in which it can radiate hundreds of milliwatt of power. It's quite huge. It's quite large in terms of the power output. Okay, and they say that LED is making a conversion from current to light as effective as 10 times more than the best LED that we have in the market. Okay, so this is a comparison between the laser diode and the LED. The light conversion from current to light is very effective for the case of laser diode as compared to the LED. So it's given here that the total efficiency of a laser diode is given by this ratio. Okay, so efficiency is given by the total number of output photons divided by the total number of injected electrons. So about photons, I think we have learned in our lecture 8, before the semester break, in which we understand how the photons were generated in the laser diode, which is through this stimulated emission, and also through this I can say that it is what you call that stimulated emission, and another one is spontaneous emission. Okay, so that's how the photons were generated in the in the laser diode. As compared to the LED, it is just based on the spontaneous emission. Yeah, right. So it can be said that for the case of laser diode, due to this, uh, I can say two methods of photon generation, spontaneous and stimulated emission. It will then produce a very high number of output photons, and as such, the efficiency of a laser diode is bigger as compared to the efficiency for the LED. Yeah, right. So about the external power efficiency, so I think we have learned about these terms before in the LED. Yeah, we are also using the same terms here for the laser diode, which is the external power efficiency. Yeah, that's a symbol for external power efficiency. So basically, external power efficiency is a parameter which is used to measure the ability, yeah, or the efficiency of the device in converting the electrical input to the optical output. Yeah, means that from the electrical input value to the light. Yeah, to the light. So it is given by this equation. So we are given the same equation that we have learned in LED before, okay, in which the efficiency is given by the emitted power PE divided by the electrical power that is used to to I can say to uh, supply, yeah, that supply the power to this laser diode, yeah, and the emitted power, and sorry, the P is given by this equation, the I and V, where I and V, both of them are the forward voltage and the forward current, yeah, supply current and supply voltage to the laser diode. Okay, so basically that is the equation that can be used to calculate the external power efficiency, and it can also be written to be equal to this, yeah, where the NT here, sorry, the theta T is total efficiency, yeah, this is the eta T, total efficiency. EG is the bandgap energy, okay, bandgap energy, and the V is the voltage supply to the laser diode. Yeah, so basically to find the external power efficiency, we can use this equation here, yeah, which can be applied to measure the efficiency of the laser diode in converting the electrical input to the optical output. Okay. Okay, number four is coherency. Okay, coherency. So we have learned before in lecture 7 what is meant by coherent. Yeah, coherent is a case whereby the light is said to be having same phase, okay, and about same frequency. Okay, so as such, it can be said that for the laser diode, yeah, the light is coherent, yeah, and it can be said that the light are said to be in phase, yeah, so the light oscillation are said to be in phase, and this is basically due to the stimulated emission. So we have agree that this particular coherency of the light source or coherency of a laser diode is basically or ultimately due to the stimulated emission, yeah. Okay, for number 5 is the emission pattern. So the emission pattern of the laser diode basically affects the amount of light that can be coupled into the optical fiber. So basically this is similar to what we have discussed before in second characteristics. Yeah. So we have agreed that for the case of the emission pattern for the laser, the emission is narrow. Yeah, that's why the light can be easily coupled into the optical fiber. Whereas for the LED, the profile of light is according to this profile of Lambert-Eaton, okay, and this is why it can be said that the light is not effectively coupled into the optical fiber. Okay, that is why it can be said that in in the actual application for the LED, it is basically used to be used in the launching, I mean, light coupling into the multimode fiber. Okay, whereas for the laser diode, it can be used for a light coupling into a single mode fiber. Okay, because we know that for a multi-mode fiber, the core is large, yeah, which is about 60 micrometer, yeah, 60 micrometer as compared to single mode fiber in which the core size, the diameter is very small, which is about 7 or 8 micrometer. Okay, so for this particular case, due to this well-directed or narrow radiation profile of the laser diode, so the coupling into the signal fiber is made possible, yeah, because the size, yeah, the size or the spectral width or the line width of the laser diode is very small as compared to the LED, yeah. Okay, so these are the characteristics of laser diode light, or the light produced or emitted by laser diode. Okay, and we did few comparisons with the light emitted by the LED. Yeah, so hopefully you understand these topics clearly. Okay, so this is the actual comparison between the LED and the laser diode. Okay, so in short, we can just say number one is the output power. Okay, the output power for the case of LED, it is linearly proportional to drive current, whereas for the lasers, it's proportional to the current above the threshold. Okay, this can be based on the graph that we have seen in lectures before. Okay, right, and we have agreed that for the case of a laser diode, okay, that should be the profile of the uh, I mean the what I call that, the uh, proportionality between the voltage and the current. Okay, it's a linear for the case of LED, but for the case of lasers, so yeah, for the case of lasers, if you can recall back, we have I, we have the V. Okay, we have a spontaneous emission, and then we have a stimulated emission region. Yeah, so this is two regions for the case of laser diode. So we have a region of spontaneous, sorry, stimulated emission. Yeah, this is spontaneous emission. Sorry, spontaneous emission. Okay, and for this it is a stimulated emission. Yeah. Okay, this is stimulated emission. So you can recall back. You can refer to this to the notes that we have covered before. Yeah. Right. For the case of current, the drive current for the LED is about 50 to 100 milliampere peak, whereas for the lasers, the threshold current, okay, because for the this is based on drive current, for lasers it's based on threshold current, it's about 5 to 40 milliampere. Okay, so the coupled power for the LED is moderate, but for lasers it's very high. The speed is slower for the LED, yeah, but for the lasers it's faster, right? Then we have the output pattern. Okay, output pattern is higher for the LED and lower for the lasers. Lasers for laser diode. I'm not sure what is meant by output pattern here. So somehow, I'm not sure about this. Yeah, I'm not sure. But sorry for that. Yeah, but I believe that this is somehow related to this what we call that. I can say the angle. Yeah, it's more towards the angle of the output pattern. Yeah, or output radiation pattern. I can say it's about that. Okay, never mind. Okay, for the bandwidth, we have a moderate bandwidth for the LEDs and a very high bandwidth for the lasers diode. Okay, then we have a wavelength available for the LEDs is about 0.66 to 1.65. So this is the range for the available wavelength for the LED, whereas for the lasers it's about 0.8, 0.78 to 1.65. Okay, that should be the range of the wavelength available for the lasers. Okay, so for the spectral wave, for the LED is quite wide. Yeah, it's wider. It's about 40 to 190 nanometer full wave half maximum. Okay, so I believe that we have learned about full wave half maximum. What is mean by full wave half maximum is about, if you can recall, yeah. So this is 100% the peak. So full width half maximum is 50% of power. Okay, this is 100% of power. So 50% of power. So that should be your uh, delta lambda. So that's what we call as full width half maximum. Yeah. So for the LED, so it's quite wide. It's 40 to 190. Whereas for the laser, it's quite narrow, which is up to 10 nanometers value of full width half maximum. So it's very small. Okay, so this is similar to what we have discussed in the previous slide on the spectral width of a lasers, which is small as compared to the LEDs. Yeah. Okay, so for the fiber type, as I mentioned before, LEDs can only be used with the multi-mode fiber, but for lasers can be used for both single mode and also multi-mode. Okay, so the ease of use for the LEDs is easier to be used, but for lasers is quite, I can say it's not harder. It's a bit hard lah. It's not very much. Yeah, not very much complicated. Yeah, not very complicated. Okay, so the lifetime for LEDs is longer because of lower complexity in terms of the circuits, whereas for laser, not that long as compared to the LEDs. Yeah. So it's about the cost, okay? So the LEDs will be cheaper as compared to the lasers, yeah? So this is just a comparison, a short comparison between the laser diode and the LED. Okay, so in communication, in our optical communication, basically we have two types of lasers that are commercially used. The first one is what we call as a Fabry-Pérot, yeah, Fabry-Pérot laser diode. Okay, so the name of Fabry-Pérot basically is from the cavity, yeah, from the cavity, which acts as the Fabry-Pérot resonator. Okay, that's why we have the name of Fabry-Pérot laser diode. Okay, so this is the sample of the figures, yeah, the diagram of your Fabry-Pérot laser diode. Okay, so we know that the characteristic of laser diode is that it need to have a cavity. Yeah, the cavity is where the stimulated emissions happen. Okay, and the light is said to be reflected back and forth because the wall of your cavities is highly reflected. Okay, highly reflected. Okay, so for the case of Fabry-Pérot diode, the cavity is called as Fabry-Pérot resonator. Yeah, that's why the name of Fabry-Pérot laser diode. Okay, so this is the sample of the light spectrum, yeah, light spectrum produced by the Fabry-Pérot laser diode. Okay, you can see that the spectrum is very small. Okay, this is similar to what we have discussed before when we learned about the delta lambda. Remember delta lambda? Okay, so delta lambda is given by this, right? Given by this difference between the wavelengths. So we can basically calculate the delta lambda based on the equations that we have seen before. Okay, and then we have a second types of laser diode which is used widely in communication is a distributed feedback, a DFB lasers. And for the DFB lasers, the resonators, yeah, the optical resonance structure here is due to the incorporation of Bragg grating, or it can be seen as periodic variations of the refractive index into a multilayer structure along the length of the diode. So if we base on this diagram, which shows your distributed feedback laser diode, the FP lasers, can we see that there is a resonators, yeah, which is active layers and also the confinement layers, and noted that there is a corrugated feedback grating. Okay, so this grating is also known as a Bragg grating or periodic variations. Okay, and the FB is based on the existence of this corrugated feedback grating. Yeah, that's how the DFB is said to function. Yeah, based on the existence of this Bragg grating. So I'm not going to go into detail on how these lasers are functioning. Okay, so we just understand, we just know that in communication, for a commercial application, so we have two types of lasers. The first one is Fabry-Pérot, and the second one is DFB or distributed feedback lasers. Yeah. So if you're interested about these lasers, you can always refer to the textbooks. Yeah, in order for you to understand more about these lasers structures and also how it works. Yeah. Okay, so this is spectrum of the DFB as compared to what we have learned, what we have seen previously for the case of Fabry-Pérot is a diode. Yeah, right. Okay, so this will be the way on how the light can be coupled from the laser diode to the optical fiber. Okay, so we have this is your laser diode, the LD is here. So we have the circuit, the driving circuit for the laser diode, where supplied current and supplied voltage is given by I and V. Yeah, so this is supply current and voltage that shall be used to drive the circuit. Okay, and from what we have learned before, Okay, the external power efficiency is given by the PE or emitted power divided by P. Yeah, this is the P, the same P here. Okay, with the same P. PE over P times 100% as given by this equation, right? We have seen this equation before, right? And then we see that the light emitted by the laser diode is a PE, yeah, the emitted power. Okay, so basically from these equations, if you know the value of external power efficiency, we might be able to calculate the value of PE, yeah, or the emitted power. And then similarly, from what we have learned previously in lecture 7 on how the light was coupled to the optical fiber, we have been using this equation before, right? Where the PC is the coupling power into the fiber optics. And this is the coupling efficiency into the fiber optics, yeah? I can say that this is a coupling efficiency, yeah, efficiency into the optical fiber, and it is basically based on the value of PE. So PE is the emitted power from this laser diode. So in order for us to calculate the amount of coupling power into the fiber optics, we need to use this equation, yeah, where this is your coupling efficiency that need to be multiplied with the emitted power, which will be then enable us to calculate the value of coupling power, yeah, right. So this is the things that need to be understood, yeah, on how the light from laser diode can be coupled into the fiber optics. Okay, so let's have a look at this example about this laser diode. So we are given a case of injection laser, which is having a gallium arsenide active region, okay, and given to have a band gap energy of 1.43 electron volt. Okay, that's the band gap energy, the EG, yeah. So that should be your EG. Okay, the question is estimate the wavelength of optical emission from the device and determine its line width in hertz when the measured spectral wave is 0.1 nanometer. Okay, so this is about the laser diode having the band gap energy of 1.43 electron volt. So based on this, we need to calculate what should be the emitted wavelength from the gallium arsenide laser diode. Okay, that's the first one, is to calculate the wavelength of emission. And number two, we need to determine what is the line width, yeah, line width in hertz, if the measured spectral width is 0.1 nanometer. Okay, so let us calculate the wavelength or the emitted wavelength from this laser diode. So to calculate the emitted wavelength, we have learned this equation of lambda equals to 1.24 divided by Eg. Okay, I believe that we have learned these equations before. So these equations enable us to calculate the value of wavelength, the lambda, if we know the band gap energy for that particular material. So in this particular case, your gallium arsenide material or active reagent is having a band gap of 1.43 electron volt. So as such, you can calculate the lambda, which is 1.24 divided by 1.43, and the value for this lambda will be equals to 0.867 micrometer wavelength. So that should be the lambda. That should be the wavelength of emission produced by the gallium arsenide having the band gap energy of 1.43 electron volt. Okay. Then the second question is to determine the line width in hertz, and in this particular case, we are given that the measured spectral width is 0.1 nanometer. So what is the spectral width? So if you can refer to the previous slide, the spectral width is equals to delta lambda. Okay, and we have learned from our lecture before the semester break, yeah, we have learned that the delta lambda can be calculated by using the equations of lambda naught squared, which is the peak wavelength, divided by 2 of NL. Okay, so we have this equation before, right? Right, so from here, we can use it to calculate the NL, yeah, because we know the delta lambda, which is given to be 0.1 nanometer, And also we know the emitted wavelength or the peak wavelength from the previous questions. Okay, so from here we can calculate that the 2NL shall be equals to lambda naught squared over the delta lambda, and you're going to have a 0.867 micrometer squared divided by a delta lambda, which is equals to 0.1 nanometer given in the question. So when we work out for this, the value for 2NL shall be equals to 0.00756, yeah, 756, yeah, that should be the value for your 2NL. So this 2NL, this value of 2NL, where N is the refractive index of the active material, L is the length of your cavity. So these terms shall be used in calculating the line width, okay, because we have learned previously, yeah, about the same topics of this, that the line width in hertz can be calculated based on the equations of delta F equals to C divided by 2 of NL, yeah, where C is the speed of light and delta F is the line width in hertz. So from here, by using the 2NL value from the previous calculation, we can see that now the 2NL shall be equal to C over the delta F, which is 3 times 10 power of 8 divided by delta F. Sorry, my apologies, my mistakes here. Sorry, my mistake. Sorry for that, yeah. Okay, it is my mistake. Okay. Right, so basically we can straight away find the delta F which is to be obtained, which is 3 times 10 power of 8 divided by 2NL, which is 0.007516. So the answer for this delta F, you can have it to be equals to 39.91 gigahertz. So that's how we calculate the line width in hertz when the spectral width is given. Okay. Okay, so this is basically according to the topics that we have learned before the semester break, yeah? Right, so next question is about the efficiency, okay? So we are given the efficiency of the injection laser or laser diode, also using the gallium arsenide active region, which is given to be 18%. So basically this 18% is the total efficiency, yeah, the eta T, which is 18% or equals to 0.18, right? All right, and then it's given that the voltage applied to the device is 2.5 volt, so V is 2.5 volt, yeah, and the backup energy for gallium arsenide is 1.43 eV, so we have the EG equals to 1.43 electron volt. So based on this, we need to calculate what should be the value of external power efficiency. So this is straightforward questions, yeah. So we have learned from the previous topics, previous slides, that the external power efficiency, the eta EP is equals to power emitted divided by P times 100%, or it is equals to eta T, the total efficiency, multiply with the EG and divided by the voltage supply times 100%, yeah? So by calculating these values, you're going to have 0.18, which is the total efficiency of the laser, multiplied with EG, which is given to be 1.43, and then we have the power supply and the voltage supply to the device or the laser is 2.5 volt. So for this, you can calculate that the external efficiency value for this laser diode is equals to this is time 100%, yeah? So it's equals to 10.2% of external power efficiency. Okay, means that the conversion of light from conversion of light from its electrical power is about 10%. Yeah, it's about 10%. Okay, so hopefully by this you have understand very well about the topics of laser diode, okay, and also on calculation of the efficiency of laser diode. Yeah. Right. Okay, so that's the end of lecture 8, and that is the end of chapter 4 on the optical sources. So by right, we have covered two types of optical sources in optical communication. The first one is the LED, which we have learned very brief on the fundamental, on the principle of laser, on the LED, and also a brief understanding on the laser diode principle. Okay, so also the characteristics of the LED and also the laser diode, yeah, and also on the coupling, yeah, on the coupling, a power coupling from the devices, from the both LED and laser diode to the optical fiber. So these are the topics, the things that we have learned in chapter 4. Okay, right. So with that, I end the lectures for this session. Okay, thank you very much. I'm going to see you again in lecture 9 on chapter 5 of optical detector. Okay, thank you very much and see you again soon.